Today we're talking about what happens to open file connections when we call fork and split a process. Welcome back, everybody. Today we're talking about processes, fork, and open files. And this topic came from a conversation I was having with my daughter the other night. That's just what we talk about in our family, I guess. But she asked, what happens if I have a process with an open file and that process forks? If the child process closes the file, does that close it for the parent? And in the moment I had a guess, but I hadn't really tried this out in a while or maybe ever. And so I thought, hey, what a fun idea for a video. Before we dive in, I do want to say this video will contain source code, as with most of my videos, and you can get access to source code through Patreon if you're interested. And to all of you who have supported this channel, either through Patreon or buying merch or however, a big thank you. Thanks for helping me do what I'm doing. But that's enough of that. Now let's jump into the code. Okay, so let's start out with this simple program right here. Okay, and the question we're looking at is what happens with open files. So let's start by opening a file here. Just make a file pointer, call it FP, and let's open a file by calling fopen. Let's call it test.txt, and I'm going to open it for writing, because why not? And also, if you're new to this, this will also create the file if it doesn't exist. And then once we have the file open, then let's come down here and simply write something into it. So let's use fprintf. We'll write to this file, and let's just say hi. So that's pretty straightforward. Now, if I ran this code right now, you would basically just get a single line like this in the file. In fact, let's test it out. So if I make this example and then run it, oh, I forgot to save it. We'll make the example and then we run it. Then you can see the file shows up, and sure enough, we get a single hi in that file. Okay, so nothing crazy about that. Now the question is, what happens? Okay, we got this file and it's open, and what happens if we come in here and call fork? Okay, so what I'm gonna do here is let's just put this in an if statement, because I wanna do something slightly different in the child process and the parent. Also, I do have a few videos on fork. If this is brand new to you, check those out if you haven't seen them. I'll put links down in the description. But for this video, it's just important to know that the fork is the system call on Unix style systems that splits a process in two. So this is where new baby processes are made. So here what I'm doing is I'm checking to see, did fork return 0? If it did, that means I'm in the child process. And what I want to do if I'm in the child process is simply come down here and let's fprintf again. And let's say child. Okay, so we're just going to add this child statement in here, and then let's close the file. Okay, so now in the parent, so we'll put that in the else over here. Then what I'm going to do is first thing I'm going to wait null. So that's going to wait for the child to finish. So I'm going to wait. I want the child to run first. And then I'm going to come down here and do the same thing we did before in the child. We're going to do it in the parent, but I'm going to print out parent. I'm going to write parent to the file. Okay, so that's what we have here. Now the reason that I want to do this is basically what I want to do is to have the processes fork. So they're going to make two different processes. The child is going to go first. It's going to write something to the file, and then it's going to close that file. And the question is what happens when it closes the file? Does that close it for the parent as well? And we're going to find out, because down here, basically after it's done waiting for the child to finish, then the parent is going to try to write something to the file, and then it's going to close it itself. And so at this point, what do we expect to happen? Well, normally with fork, what happens in the child stays in the child. They are two independent copies of each other. So we might think, no worries, we're just closing our own copy of the open file handle, but reading and writing to files has to go through the kernel, and there's just one file on disk. So at that level, it's still the same single file. So one might think maybe the file closing actually happens inside the kernel, and so maybe when one closes, it closes for the other, or something like that. Okay, so let's see what happens if we just go ahead and we compile it. Okay, yeah, I've got a couple other examples. We'll get to those in a second, but if we run it, it's gonna run. Let's check out our test file, and that might not be what you expected, right? You might say, that's a little bit weird. We get the child and parent statements just as we expected, but we're getting hi twice. So what's going on here? Why are we getting two different highs? Because we saw that this fprintf happened before the fork, so shouldn't that just be one? There was only one process at the time that called this line. Now what happened here is buffering. When we called printf, that hi went into printf's buffer, or fprintf's buffer, buffer, but it wasn't actually pushed to the file. It was still hanging out in the process's memory in that buffer. And then fork copied that memory. So you got a duplicate copy. And then when the buffer was eventually pushed to the file, both copies from each process were pushed to disk. So that's probably not what we wanted. And in a real program, this behavior could be a bit hard to predict because we may not know how libc is choosing to buffer things. Buffering is something that happens to try to speed up our programs, and that buffer size could change depending on the whims of libc. So for our example here, one way to fix this is we can come down here and put an f-flush here. What this is saying is right now, anything in the buffer, flush that to disk. Just get it to disk, and then we're gonna fork. So now if we come down here and we compile, oh, I need to save. I keep forgetting to do that. If we compile and then I run it, now if we come back in here, you can see we only have one high. Okay, so that's interesting. And also we did answer the question that after the fork, both processes have copies of the file descriptor. And if one of them closes the file, that does not close it for the other. So output from both of these processes, both the parent and the child, are going to end up in this file. So that could be an interesting option if you ever have output to a file going, you want to spin off a child process, and you don't want to have to use some other form of inter-process communication to get data from the child back to the parent. You could just have the child dump the data directly into the file, and you're going to be fine. Okay, so let's look at another example really quick. I'm going to jump over to this example 2. So this is basically the same thing, only instead of using fopen, it's going to use open, and it's going to use write instead of fprintf. Now I've talked about the differences between these in future or in past videos, but for this example, the key difference is that there is no buffering, right? So open here is not doing any buffering. It also doesn't return one of those file pointers. It returns an int, which is a file descriptor. And if I'm using open and I'm using write, these are not buffering at all. So there's no need to do any kind of flushing, right? So if you look, everything else is basically the same. Excuse my magic numbers here. I've just hard-coded these for simplicity because I was throwing this together really quick. But so if I come down here, make sure it's all compiled, and we run example 2, then down here, we're gonna get the exact same thing. Hi, child, and parent, no duplicates, and I didn't need the flush. Okay, so those examples give us a good idea of what happens when we write and then we close, when the child process closes. Now, I do want to also, I think it's interesting to look at what happens when we try to read from two descriptors at the same time. So for this, I want to jump over to this one. Let's create yet another example. Okay, for this example, let's actually just take the same thing we did over here in example 2 really quick. I want to do this. We'll just come down here and grab this because we want to do pretty much the same thing. I want to use open, not fopen, because I don't have any buffering. I don't want anything getting in the way of seeing what's actually happening between my process and the operating system if I can help it. So we'll come down here, we'll basically open this up. Let's read something a little more substantial. I don't want to read these little 3-line files. So let's come in here and let's read the source code. So do example 2.c. Okay, I'm also going to change this to read only, and I don't want to create it, assuming it is already there. And then the rest of this can be the same. Okay, now at this point, I have a file descriptor for this file, and now I want to come down here and fork. So what I'm going to do, let's come down here, and this I'm going to do it slightly different. I'm going to have a PID T called PID, and I'm going to save that for later because up front, what I want to do is kind of the same thing in both of them, right? So here we're going to split the processes and let's declare a couple of variables. So I'm going to make a buffer that's going to read in the contents of a file. So let's say int buff size, and we'll start it out at 1024. I'm going to resize it if it needs more, but I'm not sure if it'll need more. Anyway, let's also make an int that will keep track of the number of bytes we've read. Start that out as 0. And then let's come down here and let's create a character pointer, call it buff, and we're going to allocate some space using malloc, and we're going to malloc buff size bytes. Okay, so we're going to start out with 1024 bytes here. That's going to be the size of the buffer that we're going to read stuff into. Okay, so now it's time to actually read stuff into that buffer. So let's come down here and I'm going to read basically a byte at a time into the array. Okay, so we'll do while and then read fd. So this is just like write, it's read, it's unbuffered. So then we'll do like buff plus num bytes. So just a little pointer arithmetic to get the location in the array that I want. And then we're going to read 1 byte at a time. And as long as that returns 1, then we know we actually successfully got one. And then after each one, we're going to increment our num bytes. Now you might wonder why I'm reading a byte at a time. This is on purpose, okay? It's often slower to do it this way. In many of our projects, we would try to read in like larger chunks at a time, but I'm doing this because I want to encourage the processes to interleave while reading concurrently. And basically, if there are any problems when you try to read concurrently from two copies of the same file descriptor that are basically accessing the same file, well, the more concurrent interleaving we can get, the messier things are going to get, if it's going to be messy at all. Okay, so we've incremented the number of bytes here, and then I also want to just add a quick check that if the number of bytes, if num bytes is greater or equal to buff size minus 1, then I'm just going to double the size of my buffer. So we'll say buff size star equals 2. Okay, so we're going to multiply it by 2, and then we will just use realloc to resize the array. Okay, so buff equals realloc. We'll pass in buff and the new size we want, which is buff size. So that is going to basically grow our buffer to twice its original size, or twice the previous size. And then because I know I'm eventually going to want to print this out after each time I read, this is a little unnecessary. I could have done this just at the end, but I'm going to come down here and say buff num bytes equals 0. Sorry, type 0. Okay, so basically what this is doing is just saying, I know I'm going to print this out, so let's make sure that it ends in a null character. Okay, so each of our processes, each of our clones are going to do this same thing. They're just going to read as fast as they can from 1 byte at a time from this file. And then once we get down here at the end, what I want to do is to see what each of the processes came up with. So now we'll say if PID equals 0, so if it's the child, we're going to come down here and say printf child, and then we'll print out %s and a new line character, and that is going to be the buff. And then down here we will have else, and we will do the same thing but with the parent. Okay, so they're almost exactly the same. The only thing we're doing differently is printing out child for the child and parent for the parent, so you and I can tell which one is which. And then both of them, after they do this, are going to come down here and close the file descriptor. Okay, now the question is, what do you think is going to happen? Once again, it may not be obvious. Processes, again, are clones. But again, the question is, what was copied and what will be shared? What will still be shared? Will each process end up with a full copy of the code from example2.c, this file we're reading from? Are they all going to get basically a duplicate copy of the source code, or are they each going to get partials? So to find out, we'll come down here and we'll save first, compile it, okay, and then we will run it. And sure enough, it turns out that it is the latter. The current read location, so your bookmark in the file that keeps track of where you left off reading, this is clearly still shared between these two programs. These two processes basically are still sharing that same bookmark. And so some of the bytes are going to one process. I'll size this up. Some are going to one process and some are going to the other. And of course, we end up with fairly unintelligible junk. And I mean, we can sort of still see remnants, right? This kind of looks like some includes up here. We can see some remnants of our program in here, but this is probably not something that you would actually want in a real program ever. And note that if these had been two independent programs that I just started independently and they both had called open on this file, they would each have read the entire contents of the file. They would get their own copy. But in this case, if we fork, so we're basically copying a shared file descriptor and then both try to read from the same clone descriptor, then we don't get complete copies. So I hope that's interesting. I hope that helps you see a little clearer what happens when you fork. Or maybe it was just a fun exercise. Maybe you learned something new. I hope you did. If you did, please try to find some way to help support this channel. If nothing else, click something on your way out and tell a friend. And until next week, I'll see you later.